Okay, before we start with the lab, I wanted to do one problem. This is actually one of your homework problems that some students asked me about. I think seeing a problem being modeled more than just, we did really quick in class and had Edward explain how to do one problem will help you to understand and be able to do more. Now, if you need more modeling and more help, please come to my office, right? I am more than happy to help you learn. And of course, we also have Jordan as a TA to help you. So I'm going to do this problem. Before I do, I've had a couple students who talked to me about problems with the reading quiz questions. If you have a reading quiz question that you think is flawed, here's two examples that students gave me. One was it refers to a graph that's not present. Well, you can't answer correctly on a graph that's not present. Okay, what was yours, Edward? Because I don't remember what yours.
Like, is this object speeding up or slowing down? And
okay, so yeah, that's so if something like that's missing, and Edward did send me something, but send me something so I can identify what the problem is and put it in my excluded list so it won't come up as a review question for you later, as well as fix your grades for the ones that were problems. So make sure you let me know of those and send me an email so I can remember it and get it fixed. So getting on with doing a problem. So this is one of the homework problems. It's homework for problem 1, the first problem of the assignment that's due tomorrow. So a swimmer balances almost straight up from a diving board and falls vertically feet first into a pool. She starts with a speed of, and if it's in red, you know that's going to be different for everybody, 4.8 meters per second, and her takeoff point is 1.6 meters above the pool surface. Now, I want you to develop habits that will help you do the problems quickly and efficiently and correctly. Sometimes you don't need to do all these things. On those last 5 questions on the test, you will need to do them. So the first thing to do for a problem like this, remember the steps I had for solving problems? Draw the picture. Now notice it said almost straight up from the diving board. Why didn't it say straight up? Yeah, she would have landed on the diving board. That kind of would have been a problem. Now, she is staying vertically, so she just would have been balancing, but we wanted to go into the water. So they say almost straight up, and that's kind of physics code for pretend it's straight up, but yet she doesn't hit the diving board on the way down. So we're going to treat this as one-dimensional motion. That one-dimensional is up and down, and because of that, I'm going to set a vertical axis, and I'm going to call that vertical axis Y. So I drew here an arrow with pointing up and Y. That indicates that my Y direction is going up. And then I'm going to draw a picture. So we have the diving board. And on that diving board, we have a swimmer. And then we're going to have her motion. So she's going to go up, come back down, and she's going to land in the water. Now, when I did this with people before, I made my reference point the height she started from, or excuse me, the height of the water. But after reading through and doing the whole problem, I'm going to switch my reference point. I'm going to make my reference point for vertical position that she starts at a height of 0. So I'm going to put here y sub 0, her initial height, equals 0. And so if she starts at a height of 0, what is her final height? Right, it's going to be minus the 1.6 meters because it's 1.6 meters below and up was positive. So I've got the heights. It tells me the initial speed. So I'm going to put somewhere out here, the initial speed is equal to 4.8 meters per second. I put it positive. What does it mean if I put that as a positive speed? It's going up. Now there's one more variable that we know that wasn't specifically stated. The acceleration. As she's flying, she's going to have an acceleration in the y direction. These are all in the y direction. You don't have to put y. Now, if I leave it like this, it's wrong. Why is it wrong? Because she's going down. The acceleration, is downward. Now, how does the acceleration vary as she goes through her flight? It doesn't. Now, this is something that people often get confused with, especially because we know in our car, when you hit the accelerator, you go faster. And we start to think of acceleration having to do with speed. It does, but it only has to do with the change in speed. So when I take this ball and I throw it up, the instant after it leaves my hand, when we have questions and it says, when it leaves the hand, we mean as soon as it's broken contact with the hand, okay? Not while it's still in contact with the hand, because things are changing when it's in contact with the hand. As soon as it leaves the hand, it has the acceleration due to gravity that's downward at 9.8 meters per second squared. What happens to its speed as it rises? It's going to decrease in speed because the acceleration is the opposite direction of the velocity. When it gets to the top, what's the speed at the top? It's 0. And then when it comes down, the speed is increasing downward. What's the acceleration direction when it's coming down? Downward. Negative, by negative you mean downward, I'm good with that. What was the direction when it was going up? The direction for the acceleration. It was negative. It was pointing down. Even while it's going up, the acceleration is downward. That's why it was slowing down. Now the one that confuses a lot of people. At the height of its motion, at the top point, we said the velocity up there is 0. What's the acceleration? It's got to be 9.8 meters per second squared down still. Now, some people said 0. It's a very common answer. Because remember, I said we start to confuse speed with acceleration. But acceleration is the rate at which it's changing speed. So we all can agree that at the top point, its speed is 0. If the acceleration is 0, what's happening to the speed over time? It's not changing. So if I threw the ball up and the acceleration hit 0 at the top of its flight, what would it do? It would hover. Right, that's not what happens. Now, I have to point out difference between physics class and reality. You've probably heard jokes about, the physicist and the engineer and the mathematician trying to solve the problem of how long it's going to take for a chicken thrown out of an airplane to hit the ground. And, the physicist, it might be engineer, depends on who's telling a joke, says, well, assume a spherical chicken. Right? We don't have a spherical chicken. But we make assumptions to make our lives easier. And so for general physics level class, we make an assumption that there is no air resistance acting on this ball whatsoever. Now, is that real? No, of course not. Anyone who's played tennis knows that if you put topspin on the ball, it's going to die down, right? And so you can hit it harder and have it drop on the other side of the net instead of go sailing. That's because there is air resistance that interacts with the air. So that's a real thing. As a kid, we were driving from Modern Day Academy to Virgin Hospital Memorial Junior Academy. I would sit there with my arm out the window, playing in the air, feeling that air resistance. It's a real thing, and it can be pretty big if you're traveling very fast. But for this class, unless we're specifically told to include it, we'll assume that air is making no difference. So in this problem, we say it's minus 9.80 meters per second squared the entire time because we're saying the air is not going to make any difference. If the air made a difference, the acceleration would be slightly different depending on the direction it's traveling and how fast it's traveling. Okay, so I've got my picture. I have variables drawn with the picture. Now let's go to solving things. For how long are her feet in the air in seconds? So I'm looking for a time for the first one. I was given nothing that has to do with time, but I was given the initial and final heights, the initial speed, and the acceleration. I was given everything but time. I have to decide how to solve this. What's the method of choosing your equation? Generally speaking. It's going to be the one that's, I said, is 90% of the time because that's the one that has all the variables, and I have all of my variables here. So I'm going to use the equation that we said for 90%. I'm going to write it in terms of y because I'm doing this in the vertical direction. So my equation is going to be y final equals y initial plus vy initial t plus 1/2 ay t squared. I know everything in that equation except for t, so I can solve it. Now, when I solve it, there is, I read an article about this and said the master problem solver leaves in all the variables and doesn't put numbers in. The beginner puts in the numbers. What that's saying is we're assuming you are the beginner, that you're more comfortable putting in numbers. A lot of people, when they're in college, they feel like numbers are meaningful and variables like y are very nebulous. But once you've been working, especially in physics for a while, those variables take on a very big importance and numbers become fairly trivial. And so for me, I always do my math with the variables and then put in the numbers after I've done my math. And especially in a problem like this, where everyone's going to have different numbers, it is very beneficial to do it in, keeping the symbols there, and then you can see how things will change with variables. So with this form, we have time and time squared. How many people love an equation that has time and time squared in it? All right, Eric. So what do we do, Eric?
Set it equal to 0.
Okay, first we have to adjust it so it's equal to 0. So I'm going to just subtract y final from both sides. And what I will have is 1/2 ay times t squared plus vy 0 t plus y0 minus y final equals 0. So there I've done what Eric said, set it equal to 0, and then what? I'm going to write something here first. This is quadratic. And so we use our quadratic equation to say that t equals, if we were to put symbols, this thing here in parentheses would be a, which is confusing because I have ay within my a, and this would be b, and this would be c, and t is going to be equal to negative b plus or minus square root of b squared minus 4ac all over 2a. That's the quadratic equation. It's the equation, we have to use. It's going to give us two answers. We'll have two possible times, and we'll have to judge which one makes sense to us. Now, as Ashley can tell you, we have two answers. One's negative in time and one's positive in time. Which is more likely, that she lands in the water before she jumps or after she jumps? Makes a lot more sense that it would be after she jumps that she lands in the water. The one that's before she jumps would represent, if she came flying out of the water, how long would it take? How long before she got to the diving board would she have come out of the water? That's what the negative one is. It represents something, but it's a hypothetical. It's not something that happened. So putting in my variables from the equation, okay, I don't like that color of green. So my b is vy0, so minus vy0 plus or minus the square root of vy0 quantity squared minus 4 times, my a here is 1/2 ay, and my c is y initial minus y final, all over 2 times 1/2 ay. 2 times 1/2, I always like that. Really, really never ever put 2 times 1/2 in your calculator. That just wasted like 4 seconds of your life you're never getting back. You know that 2 times 1/2 is 1, right? Okay. So now I just have to put in numbers. I'm not going to put in my numbers because my number is going to be different than your numbers. But make sure you do both the positive sense and the negative sense, and make sure you pay attention to signs. Where is this sign going to be important? Your ay is a negative number. Since ay is a negative number, minus 4 times 1/2 ay times y0 minus y final is going to turn out to be a total positive. That is, you're going to have the vy squared plus a number. If you don't pay attention to your signs, you might end up with a square root of a negative value and be like, no solution. Likewise, on the bottom, your denominator here is going to be negative. So make sure you pay attention to these things when you're solving the problem. Now, part B, what is the height above the board? The maximum height above the board. So part B, we're talking about right there. What can you tell me about her position, her speed, her acceleration, and her time at that point? There are two of those four that you know the exact values for. What are the two you already know the values for without doing any math? Her speed and her acceleration. I hope you said acceleration. I didn't get a second one. Okay, we know the speed. What's the speed at the top position? Okay, so I'm just going to put Vy sub B, because it's part B, is equal to 0. The other one you know is the acceleration, because the acceleration was the same value all the way through. So I know the speed there. So now for part B, trying to find the height, I'm looking, well, that's a funny way of spelling looking. It was a facsimile of right. I'm looking for YB, and I know VB, VYB equals 0. So I know the initial height, 0. I'm looking for the final height. I know the acceleration. I know the initial speed, the final speed. What do I specifically not know and not care about? Time. So if I don't know about time and I don't care about time, what equation am I going to go to? So use the equation y final minus y initial is equal to v final squared minus v initial squared all over 2ay. Put the y's in there. Now in this case, my final is b, so I'm going to replace y final with yb, and what, you know what I mean. And then I just put in my numbers. So this one's going to be pretty easy because I decided to set my reference so y initial was 0. And my VYB is 0. And so I just have YB is equal to minus VY0 squared over 2AY. And then I put in my values. And each one of you is going to have a different set of values, a different answer. So there's not a lot of point in putting in the numbers. Now, you notice I don't like to put in the numbers, but I can look and see if the speed is doubled, it's going to be 4 times higher because of the relationship of this equation. Yeah.
Wait, so for the y0 and then the y0, the b y0.
Mm-hmm.
So why is the y0 0?
The y0 is not 0. The y0 is the speed at which she leaves the diving board. So that, in my case, was 4.8 meters per second.
Okay, so then.
And then the VYB was 0, because that's the speed at the peak.
Okay.
Any other questions there?
Just to be sure then 0 goes away, right? Okay. Oh, because I was looking at that.
Everything good? Okay, there's one more part to this problem. Part C.
Or shouldn't it be negative YB?
No, it was the B was final here. So y final minus y initial. And the y initial was 0. The y final was in the positive position.
Why is the Y final not 0? Is the final the top or?
I had set so y initial was 0. She starts at a height of 0.
Oh, okay.
And then in the end, in the total end of the problem, when she hits the water, she's at the y final line mark. So that's why I call this YB being the height in the intermediate. And so the intermediate height was the answer for part B. So that was final for B. Okay, the third part asks us, what is her velocity in meters per second when her feet hit the water? There are two equivalent ways of doing this. And we talked about this just a little bit last class period when I talked about James solving a problem. We now have two ways of finding her velocity. Using the answer for part A, we know the time it's going to take from when she leaves the diving board to when she hits the water. So using the equation that relates the velocity or speed with acceleration and time, I can put in that time and the acceleration and boom, I have my answer. That's the easy way. It will give you the right sign. What direction is her velocity when she hits the water? Okay, negative. She's going down into the water, not up out of the water. So it has to be negative. But that equation will give you the correct value, including telling you that she has a negative velocity. The other way is using the equation we used in part B, that is the one that has position and speed and acceleration, but not time. The one advantage to that one is we don't have to put in time, we probably round it off. Right? Because if we round off time, we're going to introduce error from that round off in the calculation. So that's the flaw with the using time. Using the other one, it gives you the exact value, but it doesn't tell you if it's up or down. You have to use your brain to say, well, she was moving down clearly when she hit the water. So you can solve it either way. So the two ways of solving part C are either V final is equal to V initial plus AYT, or Vy final squared minus Vy initial squared is equal to 2AY Y final minus Y initial. Now this here is just rearranging this equation that's in black there for the thing I want to solve for. So either one of those equations can be used. Never would I mark you wrong for using the wrong one compared to what I used. What matters is that you do it a right way, not that you do it my way. And there are other ways, like the first problem. You could have done the first problem in 2 steps and not had to use the quadratic. It's a little harder, but some people might prefer that. So I just wanted to make sure I went through and modeled doing a problem. So as you go through the homework, you have a little more experience seeing the ideas that go into this, how you decide which equation to use, how you draw the picture, and think about it. Any questions before I start with the lab? Okay, that was no. Just for the record, for the recording. So our lab today is Introduction to Motion. We are going to be doing a lab that simply has us walking back and forth and making graphs of our motion. So your motion is going to be measured using one of these. So nicely named motion sensors. If you're working in this room, you're going to have these blue motion sensors on the top. It has a slider that will go between a picture of a cart and a picture of a stick person. Which one are you? Stick person. So slide that switch over to stick person. In the other room, it's going to have a wide beam or a narrow beam. And I think wide beam is the one to use. I'm not positive. That's why they changed it to something where you're like, yes, I know which one's person and which one's cart. So that's our detector. What this does is it sends out a little chirp of inaudible sound. The frequency is above the frequency that our ears can hear. Now that doesn't mean you don't hear anything because you hear it turning on and off. So it sounds like it's sending out a click. And it's, just like a bat uses its echolocation, it sends out a chirp of sound. That sound comes up, it hits something, hopefully that's your body if you're trying to measure the position of your body, reflects back, and it measures the time from the chirp being emitted to when it gets the reflection. And then based on that time, it uses the equation speed equals distance over time to calculate the distance. Distance is equal to speed multiplied by time. And of course, you have to divide by 2 because it went out and back. So all of that's done in the computer. So it's just going to give us a distance. And so we're going to make graphs of distance versus time and try to correlate motion with what we see on the graphs. So you're going to start off by doing these 4 things. Now you're working with a partner, 2 people in a group, and I want each person in the group to do 2 of these 4. One person will walk slowly away and quickly toward, and the other one will walk quickly away and slowly toward. Now, what is quick and what is slow? Slow is, like, quick is not running. We want to keep things safe and sane in the class. So quick is just, walking like this. Okay? Don't be running. Don't be crashing into things. Safety is important. And that's recorded. So if there's anything that goes wrong, we all know I told you, be safe. So you're going to do these. I'll show you how to do them in just a moment. Actually, I'll have Alex work with me to show you how to do them. For the record, Alex is going to act like the TA today. He was the TA for this lab last year for a different class, so he's gone through it. And since I don't have a TA and this is the first time you'll be using this software, I need his help to make sure everybody's down with the software. So, yeah, he doesn't have to turn in a report. Moving on. So you're going to do these, and then you have questions about them, and then you're going to get to sketch a qualitative graph of what you think will be produced when a person does a certain motion. Now, let me emphasize, because last class period, there are some people who didn't follow along with this. You're supposed to do this before you actually do the experiment. If you do the experiment first, what's the point of sketching out what you've already seen? The point here is for you to think about what you think it's going to look like, and then to do it, and then you can have either confirmation that you understood it, or that little cognitive dissonance of, I thought I knew and I don't know. Right? If you do it first and then do the sketch, you've just wasted your time. So make sure you do the sketch first. And then you're going to actually do the start a half meter away, walk away for 3 seconds, stop 3 seconds, walk back. Now, how do you go between the description and the graph? We have the theory right here. The theory says that speed is change in position over change in time. If you walk away slowly, your position is slowly going to increase. And so you're going to make a graph with the position slowly increasing. When you stop, the position doesn't change, and so on. That's especially important when you get to comparing velocity graphs to position graphs. You don't have to do the prediction sketches until after you've done the first 4, so you can actually see in action how this works. Okay, now I'm not going to go through the whole thing, but you do have turning on the prescribed data. You're going to turn on the data. It will show you a certain path on the graph, and then you're going to say how you're going to have to walk to make that occur, and then you're going to have to walk the walk and make it happen. So Alex, come on up and we'll show them how to do these things. And by the way, a couple people asked, yes, we're going to be doing all 3 Roman numeral things. Time shouldn't be an issue here. This should go relatively quickly. So Alex is just going to be my walker. So Alex is going to start standing in front of this. I'm going to put it so you can walk down the center of the classroom and not hit a table. So you see capstone here. It's opened. It's in the distance versus time graph. To start taking data, I simply hit the record button, and he walks away, and you see the graph move as he walks. Now, one thing about these, you can stand aside until I call you back. One thing about these is we want your graphs, when you take pictures of the graphs, we want them to fill the screen. We don't want a graph like this that's just a little part of the screen. If all of my data was part of what I wanted in my picture, then this top left button, top left corner, is the go-to button. That will rescale it so all of my data perfectly fits the screen. How nice. But sometimes you don't want all of the data, you just want a piece. Let's say I only wanted the data from the hand here to the hand here. There are two ways to achieve that. One is, see this little button with a pencil and 3 dots? If I click that button, it puts this little selection box. I'm going to drag it over and make it so it covers the part of the data I want. And I can change the size of that box. And it's only the data there that's lit up with yellow. That's what it's going to scale to if I hit that scale to button now. So once again, there's a quick and easy way if you just select the data you want. The third way is putting your mouse here, and you can change the scale. Put the mouse here, you can change the scale. If you put the mouse somewhere else, see the hand? You don't talk to it. That hand will move whatever you're grabbing. So now I'm moving the purple thing, or that's not purple, peach color thing. Here I'm going to move the graph. So I can move the graph around like that. This thing up here, if you select it right, you can also move it. There we go. So you can move that around because you don't want that on top of something important. Now, how do I take a picture of this? Let me rescale it first. To take a picture, this icon here, can you see the one that is flickering off and on as I, yeah, when I put the instructions, you probably saw that. That is supposed to look like a camera. That's for taking pictures. Now, when I clicked on the arrow, it gave me some options there. The top one will take a picture of the entire page. That is, it's going to have all of the stuff on the outside. You know, it's going to have the stuff on the left that has like data, summary, the stuff on bottom, record stuff. Generally, you don't want that. The one in the middle and the one in the bottom, for our purposes, are going to be the same. If you have more than one graph, they're different. So make sure it's on either content or display. I'll just choose content. The button right beside that shows me any pictures I've taken. Right now, I've taken no pictures. I click the camera, not the arrow, but the camera, and there, I took a picture. Voila. I can check to see what it looks like by double-clicking it. The X will actually delete it. There, it's gone. I'll take it again. I can click down here to annotate, so I could, type in there that this is Richard. I'm sure there's a way of getting apostrophe here that's easy. Richard's graph. So you can label them here so you know which one is which. PG. That G is close to H, but it's not. There. So I've now named the graph. It's got a little annotation. So what it's going to print like is, I think it's down here. It'll say Richard's graph. Close Sesame. I'm going to close that. Well, before I close that, when it comes time to print them, you could print them to paper, but you know what? Since you're turning everything in as a PDF document, why not save it as a nice colored PDF to turn in? Well, to do that, you just go up here to print. And if I had more than one, I would choose the ones I want to print before I hit print. And then just do like Microsoft Print to PDF. And it'll save as a PDF. You can then, using your Gmail account, your Google account, you can email your figures to yourself and then combine them with your scans when you scan the rest of your data. If you choose to print, which I can't do here, you print to, I think it's KC 123, and it prints in the back of the room, the other lab room here, if you want to print on paper. Now, getting back to my assistant, we are going to have, after you've done some work here, down here I can delete data. There, I deleted it. I could have also chosen to delete the last run or multiple ones. You have to match a picture. So for the picture, see this little triangle that looks like a Google Drive logo? That's the one to add or not show data. I click the arrow next to it, and I'm going to turn on prescribed. That's the data that my TA is going to try to match. He's going to fail miserably. How do I know this? just the opposite. He needs to start here, which is like 0.3, meters away. Okay, so let's just see how he does blind. He didn't know I was going to make him do this. It's not like he's practiced. Okay, that's obviously a little too close, it turns out.
Close. Oh.
Okay, so there's one try. Let's say that we're not happy with that because we should be able to do better. So instead of putting him on the spot, let's put me on the spot. You start it and I'll try, and then you can all laugh at me. So based on me having him come forward and being too far forward, I'm going to start further back. Okay. See, I'm too far back. Perfect. Overshot. Okay. Neither of us did very well, right? You'll want to do it more than once so that you can lock in how to do it, right? Each of us, for a first time, we saw, oh, yeah, made a mistake. Need to pay attention, do better next time. And so keep them up there until you get one that you think is good. Then when you get one that you think is good, I can come up here and I can turn off the one that I thought was horrible. Okay, I'm joking. And I can just show the ones that I want, and then I can take a picture of it. And I can open this thing to see if I took a picture. No, I failed. There, now I have a picture of it. I can delete the one I don't want. Jared just deleted my run. So I think that was the basics of what we needed to do, right? So at this point, any questions? How many people in your, okay, Ed.
What kind of observation or hypothesis?
Okay, what kind of observation hypothesis? Question I've been asked actually multiple times before, lab. The observation needs to be an observation of something moving. And there's lots and lots of different variations on this. But you have an observation of something moving. And then your hypothesis needs to say, okay, based on my understanding of how position is graphed on a position versus time graph, or how velocity is on a velocity versus time graph, either the position or velocity versus time graph for that should look like this. So your theory there is the relationship between position and what the position time, or position and what the velocity time graph looks like. And then your test is going to be, so now I'm going to walk and do similar motions to what I saw, and if my hypothesis is correct, then my graph with this motion should look like this. So you're making, your hypothesis is relating motion with the graph, and then your test is taking that relationship between motion and graph and applying it to something different than your observation to say the graph should look like this. Does everybody understand that? How long should the observation be here? Yeah, like 2 sentences. It doesn't need to be something big, long, and hairy. It just needs to describe something in motion that you see on a regular basis, something with changing motion, not changing direction, keep it straight lines, but something that's not at constant velocity, something that's speeding up and or slowing down. Okay, any other questions?
You had mentioned that we need to get signed off before we begin the experiment?
You don't have to.
Okay.
If you get your hypothesis and your observation hypothesis and test signed off before you begin, then when I'm grading, I won't grade it. I'll just say, oh, they did that right. But if you don't, then I just have to grade it in the end. So if you do fine on it, it's no problem. But if you don't have something that's appropriate, well, then you'll have some points lost. Speaking of points and grading, before you start today, check what your grading was on the last report, not the number. I mean, all scores except for people who didn't turn in or didn't do sections are like 96 or above. That's because it's the first one I made notations And usually, even if I did say this is how much you would have lost points for most of the notations in there. So I put those in there so you have an idea. Oh, these are things I misunderstood. So look at that so you can learn from it. That's why I spent all my Sunday afternoon and Monday afternoon grading them. Second of all, remember that your data calculations and discussion section is supposed to be a chronological record of your lab. So it should, start with the first thing you do. So if the first thing you do is answer a question, that should be the first thing there. And then when you get to data, you have your data table. And if you have difficulties with your data, like you decide that Irving is just smooth as silk and Richard is super jerky and makes everything look bad on the graphs, you make a notation there about it. Right? You write what's going on. Now, one student asked me about erasing. I used to require my students to use pens, and we have a lab notebook. The reason being that when you're doing scientific experimentation, you have to be honest with what happened. And so if you take data and then you decide, oh, that data was bad, you don't destroy the data. You have to keep the data there because it could be that that data was perfect. It's exactly the way it's supposed to be, and you misunderstood. Or it could be you made a mistake. So you leave the data there. If you think there's a mistake in the data, you just put a single line through it and you make a notation on why you think that's an error and go on. I could give you examples of people I know who doing real research, well, people I know, person in my research group that graduated just before I got there, he would do experiments, and if it didn't confirm his hypothesis, I mean, this is real scientific, research. It's not contrived like this. He would throw away the data and just write in the data log, bad data. And who knows what he actually found, if he had made mistakes, or if he had done it right and he misunderstood how to interpret it. That's horrible, horrible, not acceptable scientific procedure. So don't destroy data. Write it down when you take it. If you decide it's wrong, put a single line through it and note why you think it was wrong. Okay, really, let's get started. Groups of 2. We have stations set up in the other room as well.